Hello students, in last lecture we have completed time response specifications numericals. Okay, so today we will start with error analysis. Look at this. So in error analysis we will see steady state error. Okay, see we have introduced the formula for steady state error. Okay, that is ESS is equal to limit E of t tends to infinity. Okay, so now we will see this in brief. So look at this. The open loop transfer function g of s h of s is given as k 1 plus st1 1 plus st2 plus dot dot dot. Okay, upon s raised to power m 1 plus sta plus 1 plus stb dot dot dot. Okay, so what we need to see here the important concept is introduced here, that is called as a type of the system. Okay, so what is type of the system? In any transfer function we have to calculate the number of poles at origin. Okay, so number of poles at origin will give you the type of the system. Okay, for example, look at this transfer function here. In this transfer function we know that the numerator will give you the number of zeros. Okay, so this is numerator. From numerator, when you will equate it to 0, you will get number of 0. When you will equate denominator to 0, you will get number of poles. Okay, so you can see here these are real poles. Okay, whereas s raised to power m term is there. Okay, suppose I will put m is equal to 0. M is equal to 0. So what will be term there? S raised to power 0, it will be 1. So what you will say? M is equal to 0. It means that no pole is at origin. No pole is at origin. So this m will define the number of poles at origin. Suppose you have m is equal to 1. In that case, what you will say? One pole at origin. Okay. So look at this. S raised to power m is there. So what is that term? Are the poles at origin. So this term will give you the number of poles at origin. Okay, m is equal to number of poles at origin. Why this term is getting repeated? Because see, these are the poles at origin, whereas m is the number. Okay, when you will put m is equal to 0, so what you will say? No pole at origin. Okay, when m is equal to 1, what you will say? S raised to power 1 term is there, so one pole at origin. So m will give you the number of poles at origin. So look at this, here m is equal to 0. So no pole at origin, and it is called as type 0 system. Okay, when m is equal to 1, so one pole at origin, and that is called as type 1. Okay, m is equal to 2, so two poles at origin, and it is called as type 2 system. Okay, so again I am repeating, what is type of the system? Number of poles at origin will give you the type of the system. Okay, now see steady state error. See the definition of steady state error. We have already introduced this definition, but again I am repeating. Steady state error. The steady state error is the difference between the input and output of the system during steady state. What is that input? Input is R of t. What is output? Output is C of t. So we know that E of t is equal to R of t minus C of t. Okay, so error is given by the difference of input minus output. Okay, now next look at this. This is block diagram of closed loop control system. Okay, I have written in short form block diagram of closed loop control system. Okay, so now we are familiar with this block diagram. Okay, and we are familiar with all the terms associated with this block diagram. What we need to find from this block diagram, see actually we are discussing about the error. Now what is error? Error is nothing but input minus output. Okay, now see from this block diagram we will calculate the error. Okay, so look at this, here R of s term is there, here C of s, this is called as forward path gain, G of s, H of s is called as feedback path gain. Okay, and this summing point is nothing but comparator. I told you this summing point, at this summing point two signals are getting compared. So what are that two signals? If you remember in unit 1 I have introduced the term here B of s. Okay, so what is B of s? B of s is feedback path signal. Okay, so just to avoid the confusion, now I am not introducing b of s, but you can put that term as b of s. I am directly writing. Look at this block diagram carefully. Here e of s term is there. Okay, so I have taken the Laplace transform of e of t because all the terms are taken in Laplace. Okay, so output of this summing point, that is output of the comparator, is nothing but e of s. Okay, so this is output, and this comparator is comparing two signals. One is r of s and this is the second signal. Okay, so if I will calculate the output at this point, okay, so what is output here? Look at this. This is gain into input. See the path here. Okay, signal is coming from here. Though c of s is output, but suppose I need to calculate the output at this point. So how we are calculating? Gain into input. Okay, so what is gain here? Gain is nothing but h of s. What is input? That is nothing but c of s. Okay, so at this point what will be output? Output will be gain into input. Okay, so see, e of s I have written as, look at this, e of s I have written as r of s minus c of s into h of s, because I have assumed negative feedback signal. Okay, so r of s minus c of s into h of s. Now look at this carefully. This c of s is nothing but output. So we know that the standard output, okay, or standard transfer function can be written as c of s upon r of s is equal to g of s upon 1 plus g of s into h of s. This is for negative feedback signal. Okay, but here what I am doing, I am replacing this c of s with the standard transfer function. Look at this, g of s upon 1 plus g of s h of s, multiplied it with r of s, because c of s is equal to g of s upon 1 plus g of s h of s into r of s. Okay, so I have replaced this c of s with this term, h of s is as it is. Okay, now look at this. So cross multiplying this, so 1 plus g of s h of s into r of s minus g of s r of s into h of s. Okay, so see here what I will get. Here I have the term plus g of s h of s r of s. Okay, and here when you will multiply, so this will be r of s. So see here g of s h of s into r of s, and here we have the term minus g of s h of s into r of s. So these two terms will get cancelled. So what is left in the numerator? Only r of s is left. So what I got here, e of s is equal to r of s upon 1 plus g of s h of s. Okay, e of s is equal to r of s upon 1 plus g of s h of s. Now see the steady state error. Now we are talking about only error. So we will introduce the new term, steady state error. So steady state error according to final value theorem. See, what is that final value theorem? Okay, see, we have studied this initial value theorem and final value theorem in network function. Okay, now final value theorem is given by steady state error is equal to limit t tends to infinity upon limit t tends to infinity into e of t. I am repeating, according to final value theorem, ESS is equal to limit t tends to infinity into e of t. Okay, it can be written as limit s tends to 0 into s into e of s. Okay, limit s tends to 0 into s into e of s. Okay, so see here, so I have the formula ESS is equal to, look at this, I have written in Laplace form. So steady state error is given by limit s tends to 0 into s into r of s upon 1 plus g of s h of s. See the important thing, suppose unity feedback system is there. So in case of unity feedback system, h of s it will be 1. Okay, so directly you will substitute h of s is equal to 1 here. So what you will get? You will get limit s tends to 0 s into r of s upon 1 plus g of s. Okay, so this is the formula for steady state error when h of s, that is unity feedback system, is there. Okay, so see, now in next class we have to calculate the steady state error with different inputs. Okay, see R of S term is there. Please remember this formula. ESS is equal to limit S tends to 0 S into R of S upon 1 plus G of S H of S. Okay, so R of S term is there. So R of S you need to put for unit step, unit ramp, unit parabolic. We have studied standard test signal. So we will substitute the standard value of R of S here and we will calculate steady state error. Okay, so thank you students.